So, Chapter 7, there's only, I think, 3 sections in Chapter 7, so this one is much shorter, which is why we have a quiz already next week. But there's 3 things that we're doing here in 7.1. 1, we're solving differential equations. 2, we are verifying solutions. And then 3, we're going to talk about exponential growth and decay, just like you did in Algebra 2. Same kind of thing, but we'll have a little bit different equation, and of course it's going to be calculus related. So let's start here. This is 155 in your book if you want to have that open, because there's going to be some steps, especially in terms of how to solve a differential equation. Just what is a differential equation? It's an equation that has a derivative already built into it, okay? And so what we're going to be doing is solving equations where the variables will be able to be separated. We talk about separable equations earlier in the year in order to solve them. And we're going to have the same kind of thing going on with these. Okay. And so the book, this is page 155 in your book, is where we're going to have the steps, all the different steps that we're going to take in order to solve a differential equation. And most of the time, we will follow all of the steps, okay, depending on the particular problem. But this is, again, like a general idea of how we go through and solve a differential equation. So step number 1. So here's, as you can tell, there's a box on page 155. So if you want to screenshot the box, I'm just going to go through them with you one at a time. If you want to write them down, that you certainly can do that too. So a lot of the time, the equation is going to have a y prime in it. But we're going to need to rewrite it, and that's why it says if necessary. If it's not already written as dy over dx, you're going to want to rewrite it that way. Because these equations are separable, we're going to end up separating the dy and the dx. So that's why we want you to do that. Then the second piece is multiply both sides of the equation by dx. Again, depending on the type of equation you're given. That's why I keep saying if necessary. Because, again, we're trying to separate the y's and the dy to one side, the x and dx to the other side. After that, okay, we're going to have, this is where we're going to have one side with the y's, one side with the x's. Because what we're going to attempt to do, of course, is integrate. That's where we're trying to go. And getting this part right, as it obviously said, is the most crucial step. Because from here, then we can integrate. You're going to have c to one side. Now, here's why it's only to one side. And we'll go through an example, but technically I could have like a c1 on the left and a c2 on the right. But since they're a constant, I can kind of combine them together. Because, like, for example, c2 minus c1 would be some other constant. So instead of having another c3 or something, we can just add the constant to one side, and that sort of takes care of the constant piece. And then, of course, we're going to solve for y. It says, I'm not sure why it says if necessary. Most of the time you're going to have to do that. And sometimes we can use an initial condition to solve for c. So if it's given. All right, sometimes you will end up with a c as a part of your answer, but if there's an initial condition, that's giving you the tools to come up with what c should actually be. All right, and he says 5 and 6 are interchangeable, but to be honest, I think you really want to go in that order and find c last. Okay. So again, the general idea is we're going to separate y's to one side, x's to the other, get the dy with the y's, the dx with the x's, integrate both sides, and then we will have our solution. Okay? All right, let's move on to an actual example. Now, I already went ahead and did the first step to guess I shouldn't have, but. So one of the things that you might do, so this, actually that's okay. You know, if this is the problem that you're given in the book, instead of writing it down like this, you might as well make the change right away, right? Change the y prime to dy over dx instead of writing the actual problem down. Now, I know a lot of you take pictures of the problems anyway, and so it's just there, but for those of you who choose not to do that, I would start this way, okay? And so again, what our goal is to get the x's and y's on opposite sides so that we can get the dy and dx on opposite sides. So in order to isolate and get rid of this dx, what I want to do first, which makes the most sense, is move the x to the other side. Okay, and now I can multiply both sides by dx, and I'll be left with 2i dy over here and negative x dx over here. Right, so in general, this is the strategy. Get the y's and dy on one side, get the x's and dx on the other side, and it's just algebra, okay? From here, we're going to integrate. All right, and so when I integrate this, what am I going to get? Y squared. When I integrate this, what am I going to get? Yep, negative 1/2 x squared or negative x squared over 2, either way. So we're going to integrate both of those, right? And then we just have to add in our c. And I always put it wherever I have the most room, and I typically put it to the right. You could put it over here, it doesn't matter. Okay. Again, if you wrote this as negative 1/2 x squared, that's fine. Now, in this problem, notice it asks for a general solution. They don't give us any information about an initial condition or anything like that. So this is it, almost, right? I'm not going to be able to find C in this problem. My only thing left to do is find out what Y is. Okay, so that's what our goal is. We're solving for Y. So how am I going to solve for Y here? Square root both sides, okay? And whenever we square root both sides, you have to do what? Plus or minus. Now, here's where it's a little tricky. Okay? Normally, we would just put a little plus or minus sign there and call it good. Here's the dilemma. Okay? And we'll see more about this when we start looking at initial conditions. It cannot be both. Normally, when we put the plus or minus, the inference is it's both. One's positive, one's negative. In this case, it is specifically or. It has to be one or the other. They don't give us enough information in this particular problem to determine which one it is. So putting the plus or minus is really kind of frowned upon in a situation like this. You want to separate them, okay? And I don't need you to say all of this stuff here. This is just, teacher stuff here, making sure you guys understand that it's not both, that it's one or the other. But just to be clear, that's kind of important, okay? Questions about anything we did there? In college, you'll take, if you're a math or engineering or something major, you'll take an entire course on differential equations. And they call it Diffie-Q, just so you know. All right, let's look at another one. What's different about this problem than the last problem? We have an initial condition, okay? They tell us what when x is 1, we know what y is, all right? So go ahead and give this one a try. So yeah, don't be alarmed here that you have to move stuff a couple different times, right? Because we need the dx up and the dy up, which means some other things are going to go down. That's your hint. A couple things here. And I'm going to talk about this. This doesn't necessarily apply to this problem, but since we talked about that situation where it could be positive, y could be positive, or y could be negative, when they give you the initial condition, that's how you know which one to pick. They are telling us in this initial condition that y is positive. This is not going to come up in this problem, but that's how you tell. If, like in the last problem, if they would have given us the initial condition and this was it, they were telling you that y is positive. So that's why you'd say this, the positive square root. If this was negative, then you'd use the negative square root. That's how you tell in those kinds of problems. All right. So when we start moving things around, immediately we start seeing that we're going to have 1/overs, right? So I moved the dx. That's all I did. Multiplied both sides by dx. Okay. But now I got to get the x over with the dx, and I get the y minus 2 over with the dy. And so that's what I'm talking about, the 1/overs. Okay. So I divide both sides by x. I divide both sides by y minus 2. And so whenever we have, because we're going to have to integrate this, whenever you integrate 1/over, what kind of function are we talking about? We are talking about the natural log. Okay. So integrate both sides. Be careful. Make sure that you put your absolute value. Now, in this problem, I put the c to the left. And the reality is you generally put the c with the x. I know on the last problem I said, oh, I just put it where there's more room. But that was really not true. You put it with the x. Okay? And the reason in this problem that there's a c1 and just a c is because there's going to be more c's in this problem. Okay. Now, usually when you work through this, when you start doing these problems, you'll start with a c, and then later on you'll figure out, oh crap, I need another c. So then all of a sudden this will turn to c1. Obviously, I know this problem. I did this problem ahead of time, so I knew that was going to happen. I would not expect you to know that, but if you always want to start with a c1 and you just end with a c1, that's fine. And then you can add your c2 or c3 in later. But then we can kind of go from there. Now, here's the dilemma. We've got to get this y out of here. And the way that we do that is if we make this the power with e as the base. So basically what we do is I'm trying to think of the best words to describe this. We make these the powers for e as the base. That's the best way to say it. So that's what it ends up looking like. E raised to this whole thing, this is important, on the left. Okay, and here's where we get into some crazy algebra. This whole thing is the power. Really probably should be like this. Okay. And of course, e to the natural log, those cancel each other out. Because the natural log is basically saying log base e. E to what power gives me this. So the right-hand side is no big deal, right? I just get y minus 2. The left-hand side is a little bit different story. And I'm going to use my log properties, my power properties, okay? Think about when you multiply powers together, when you multiply exponents together, when the bases are the same, you add the powers, right? So what I'm going to do is separate this out and do it backwards. Right? Because if I went this times this, I add the powers. That's how you separate a power that has multiple things in it, right? Now, why is this important? Well, remember, e is not a variable. This is a whole nother constant. E to some constant is another constant. And this is how I can get the x out of this, okay? And so here's where we're at. Now, that's where my next c comes in. This is a whole nother constant. The e and the natural log cancel. And at this point, we can drop the absolute value. So now I just need to solve for y. Actually, let's find c first. Are there questions about what I did here? Some of these log properties, some of these power properties, things that you haven't really spent a lot of time with for a while, are going to come into play as you're trying to go through this manipulation. Okay. Since they tell us that y is 1/2 when x equals 1, I can just replace those, and this is how I'm going to find C2.
Would it change your answer to get that as e to the c to 1, which took?
Say it one more time.
Would it change your answer if you kept it as e to the c to the 1, which took the natural log of?
Yeah, no, I understand what you're asking. Yes, it would, because then you would have, e c to the 1, and then at this stage, you would have to then take the natural log of both sides, and you'd get a different constant. So at this point, recognizing that this is just some crazy constant, whatever it is pretty important. Okay? So of course, this is negative 1/2, and so C2 is negative 3/2. The 1 doesn't do anything. And now I can get the y by itself. So add the 2 over, replace the C2 with negative 3/2, and there we go. Okay. A pretty normal looking linear equation. So let's think about it for a second. What is dy dx anyway? When you first learned about this, what was it? Slope, right? This is a linear equation saying y minus 2 equals, this might as well be mx. Pretty complicated way to get there, right? Because what we ended up finding was our C2 ended up being our slope. Does that always happen? Of course not. It just happened for this problem. All right, let's switch gears. Talk about verifying solutions. Now we're going to talk about some more old algebra stuff. Okay, this is where they are going to ask you to decide, is so-and-so a solution to this equation? Okay? So what we're doing, actually, here's the problem first, okay? So the question is going to ask, this is example 5 again, still in your book. Is y equals 1/2 e to the x plus e to the negative x an equation to this differential equation? Okay? A solution to this differential equation. And so again, we're thinking about our algebra days. We're going to go back to our algebra days. What we want to do is just plug this in and see if it works. Okay? But in this case, I already have y, but I do not have y prime. Okay, so we're going to have to find y prime, plug it in, y, plug it in, and see if the left-hand side equals the right-hand side. What's important about verifying solutions, and again, when I say think about your algebra days, that's what I'm talking about. We're not moving from side to side. We're going to simplify the left-hand side completely. We're going to simplify the right-hand side completely and see if they equal each other. If they do, then we're good. If they don't, then it's not a solution, okay? So my first move is going to find y prime. All right, so go ahead and find y prime from this. Find y prime from this equation. So it should be pretty simple, right? 1/2 e to the x, the derivative of that is 1/2 e to the x. This one you got a chain rule and you just have the negative in front, okay? So y prime, 1/2 e to the x minus e to the negative x. Chain rule makes that minus come out in front. So we're going to take this, plug it in here. We're going to take this, plug it in here, and see if they work. Okay, and look, I even color-coded how we're going to plug it in. How cute. Yep. Okay, and so notice here, this is the notation. Does this equal this? Okay, and so right, it's just a bunch of algebra. And so e to the x minus 1/2 e to the x, well, that's 1/2 e to the x, and e to the x minus positive. So remember to distribute, make it go to both. I can simplify this, and if I can simplify this to get it to here, then we're done. Which it is, so we're done. That's all there is to verifying the solutions. Okay. See if you can make the left-hand side equal the right-hand side. And if you can, then you're good. It's a solution. If it doesn't work out, then it's not a solution. Last, we need to talk about exponential growth and decay. You're not done. Exponential growth and decay. Back in Algebra 2, we talked about this. You've probably dealt with it in science since. But the formula looks something like this. Okay, bless you. Okay, and this is a more calculus-based form of it. We had it look a little bit different in algebra. But exponential growth or decay. Y equals C, some constant, from E times E to the KT. All right, let's define some of these things. First off, C is the initial value. Whatever the substance, however much of the substance is present at time 0. K is called the constant of proportionality. And sometimes we just call it the growth constant or the decay constant. If K is positive, then we're talking about a growth situation. If K is negative, we're talking about a decay situation. So growth meaning over time, the substance, the amount of the substance is increasing. Decay meaning the substance over time is decreasing. Okay. Usually we talk about things like half-life and carbon 15 and stuff like that for decay. For growth, a lot of times we apply financial type algorithms and situations for growth. Okay, that's not always the case. Sometimes that can be done with a petri dish too, and see how fast bacteria grows, or how often a virus reproduces, that kind of stuff. Okay, so a couple things to think about, a couple more things to think about here. Okay, T is the time, Y is the amount of the substance present at a given time. Okay, Y is a function of T. There's no X in this problem, right? In these kinds of problems. Always growth and decay is something that happens over time. All right, so here's the example we're going to do. Okay, this is example 8. Again, still from your book. Y is the mass in pounds of some radioactive element whose half-life. Okay, so we're talking about decay. Over time, half-life is 4,000 years. So what that means, just to be clear what half-life is, whatever this element is, it takes 4,000 years to lose half of it. All right. So if there were 10 pounds of it, it would take 4,000 years for it to get to 5 pounds. That's what half-life means, okay? In this case, they say if there are 200 pounds of the element in an inactive mine, how much will remain in 1,000 years? Okay, so more than a half-life, more than 2 half-lives. So you should think it's going to half itself again, and then a little bit more in terms of checking it for reasonability. Okay, does my answer make sense? So we start off, if we aren't given K, okay, we have to find K if it's not given. And in this case, it is not given. They just tell us what the half-life is. They don't tell us how it actually changes. And so we start with our normal equation. And what we have to do is figure out what K is. But because they tell us how long it takes to lose half of the weight, half of the mass, what we can do is just replace Y. What we're trying to figure out is, when is my initial amount, C is the initial amount, half of it, okay? All right, we know that the time is 4,000. It takes 4,000 years to lose half of it. And now, since I have C's on both sides, they really just cancel out. So maybe you remember this from doing algebra. The C's don't really matter. They cancel. So what I want to know is what K value will produce e to the 4,000 K equaling 1/2. And so, of course, you can think about it a couple different ways, right? if I take the natural log of both sides, I take the natural log of this side and the natural log of this side, the natural log and the e cancel, so I end up with 4,000k. So 4,000k, I think I skipped that. Oh, no, I didn't. So natural log of 1/2 equals 4,000k. If I just take the natural log of both sides, I'm going to write that in there. Okay, natural log, and that's how I get to this. And then to solve for k, I just divide both sides by 4,000. Now, as you work through this problem, this is going to give you some crazy decimal, right? I would not figure out what that is. If you want to get the best answer, do not calculate this. Use this value for your k. All right? Now, the thing that's nice about this problem is they tell us how much we're supposed to, they tell us the time that we're trying to check. This k value works for this problem for the rest of the problem. And sometimes it'll be part A, B, C, whatever. But this k will be the same for the rest of the problem. Now, the thing that's nice is when I look at this situation, we're trying to find out what y is after 1,000 years. Okay? We know that we started with 200. So I have everything I need now. Okay, we're going to solve for y. So what it ends up being is my initial amount is 200. My k value is this. I'm trying to figure out what it will be in 1,000 years, and now put this all in the calculator. Now, just because I just recently graded those tests, I finished them this morning, some of you are still having a little bit of an issue entering stuff in your calculator absolutely correctly. It's really critical to make sure that we're doing that right. So be careful with that. At this point, I'll just put that up there and see if you can get that answer. All right, it's 168.179 pounds. This place did tell us 3 decimal places. I don't know why it said 3 or more. I'm crossing that out. Please, just 3. It's always 3.